Hello, everyone. In this video, we're going to go through OWL 4. So we're going to be discussing organic chemistry. A lot of this will be what's called nomenclature, which is naming. And then we're going to go through a couple of different types of reactions. So question 1 is going to have you identify the functional group, and they want you to basically match up the functional group with the correct name. So what I did for you guys is I actually posted a picture for you to be able to look at, and basically what it is it's a basic decoding of organic compounds. So what it does is it kind of shows you those different types of functional groups. So remember that we have different forms. We have a skeletal form of organic compounds that we can see. We also can see them in condensed form, or we can see them in expanded form. When we go to look here, we're seeing these pieces in a skeletal form. So what this is showing you and depicting is that we have hydrocarbons, which are carbons and hydrogens. At each of these points, these are a carbon. And remember, carbon wants to be attached to 4 different bonds, or at least have 4 bonds around it. So what they're not showing you are the carbons and hydrogens. But what we're looking at here is this attachment to an OH group. If there are only single bonds and you have a carbon that now is attached to an OH group, this is called an alcohol. What you're also going to see is something called an aldehyde. So this is a carbon, and then we have a carbon double bonded to an oxygen with a hydrogen sticking off. This is what's known as an aldehyde. And then finally here, this is a carbon, this is a carbon, and this is a carbon. So you have 3 carbons in a row, and that middle carbon is attached to a double bonded oxygen. We call that double bonded oxygen to that carbon a carbonyl group. So this creates what's known as a ketone. And then here, what we're going to see is something called an amine. So we have a carbon that's now attached to this NH2 group. Now, there are a couple other functional groups as well that I would like you to know. So let me go through a few of them. One is a carboxylic acid. And what you'll see is you have a C double bonded O, and then there's this other alcohol group together. Be careful. Remember the difference between an alcohol and a carboxylic acid is the alcohol group is going to have a C that's attached to this OH group. There's no double bonded O. There's no carbonyl group. So this guy would be an alcohol, and this guy would be what's called a carboxylic acid. Now we have a couple other different functional groups for you to know as well. You could see something like this. The C with an O in the middle and attached to another C. This would be called an ether. Now, this can also vary. These groups here doesn't have to be a CH3. Sometimes we'll depict it with an R just to say that it's another carbon group, because this could look like, for instance, let me erase this. It could look like this. Or it could be something really, really long. But if you see a C with an O and another C, this is known as an ether. All right, so let's start off with those functional groups just for right now, and then we'll add more as we go. All right, so let's get back to our OWL really quickly. So like I said, here what we want to do is we want to identify the functional group. So as you can see from number 1, we have a C double bonded O in this OH group. That's your carboxylic acid. And we're showing these pictures in a expanded formula. So they're showing you that how the carbons are bonded to the hydrogens and how they're bonded to the oxygens. So again, what we're seeing here is a C, the C double bonded O in the middle, and then another C. This is known as a ketone group. Ketone. Oh, no. Be very careful. These things are very, very picky. Ketone. All right. We have a C another C double bonded O, this carbonyl group, and a hydrogen. This is going to be an aldehyde. All right, we have a C attached to an NH2 group. That's your amine. And then finally, at the very, very bottom, we have a C with no double bond, a single bond to this OH group. That would be our alcohol. All right, so you're going to do the same thing for question 2 and question 3. Now, question 2 is a little bit different because what they are doing is they are showing you, instead of that expanded formula like this guy here, they're just showing you that condensed formula. So what I would suggest doing is writing these out in the expanded formula so you'll be able to see the differences. So for instance, with this CH3, COOH, remember, we want to think about carbon being attached to 3 hydrogens. Because again, it wants to have 4 bonds. Then it's attached to that C. And then what we're going to notice is that we have an O and an OH group. Now again, carbon wants to have 4 bonds around it. So this becomes a double bond. And now we can go look for that functional group. It's that C double bonded O, OH. That is going to be your carboxylic acid. Down here, we can see that we have, again, that carbon attached to hydrogens. All right, and then we have CH2. And then we have that NH2. Now remember, if you see a C with an NH2, we're dealing with an amine. All right, next one, we're going to have that CH3, C, CH3, and that oxygen is going to go up here. Now again, because carbon wants 4 bonds, we're going to see a double bond here. You have those 3 C's in a row, and then you have that double bonded oxygen in the middle, this carbonyl group. That is our ketone. All right. So CH3, CH2, OH. Again, we have single bonds and we have this OH group. That is our alcohol. And then finally, the last one would be an aldehyde. So let me show you why it would be an aldehyde. We'll see CH3, C, and then what's going to happen here is the reason they depict it in this format is to show you that the carbon is attached to the hydrogen and to the oxygen. And so now we can see those 4 bonds of how this is sort of set up. This guy here depicts the aldehyde. So I hope this makes a little bit more sense. All right, question 2, we're going to care about what kind of hydrocarbons we're dealing with. So hydrocarbons is a very fancy word for containing carbon and hydrogen. And again, this is one of the reasons that we will say that it is going to be an organic compound. So what you're going to see are these arenes, which are going to show you these ring-like systems. If you see your compound in a ring, it could look like this, it could look like this, it could look like this, but that's called an aromatic compound, and we call it an arene. And sometimes you're also going to see a very important aromatic compound called benzene. Benzene is going to be this nice bonded form, and you're going to see that it has alternating double bonds and single bonds. Now, when we depict single bonds, we show 1 line. If you see 2 lines, that's a double bond. And if you were to see 3 lines, that's depicting a triple bond. This is showing us that these guys are sharing the electrons. And the electrons are shared within this line, if you will. Imagine that there's 2 electrons per line. So the first guy is, if we see all single bonds, they're called alkanes. And so down here, we would see an alkane. If you see a double bond, it's an alkene. And if you see a triple bond, you are dealing with an alkyne. Now, we also care about whether or not they're saturated or unsaturated. An alkane is saturated, and it's saturated with hydrogens, meaning that it has the most hydrogens possible around that carbon atom. There are 4 bonds that we're going to see around that carbon, and it's all going to be these single bonded hydrogens, so it's saturated. Alkenes and alkynes are considered to be unsaturated because they have those double bonds, so they don't have as many hydrogens around them as they normally would. So what we're going to do for this portion here is we're just going to state whether or not it is an alkene, alkyne, an arene, which is that aromatic compound, or again, an alkane. This guy is all single bonds for number 1. It's an alkane. This guy, for number 2, has that triple bond. You're dealing with an alkyne. This guy here has a double bond. It's an alkene. And then finally, triple bond, we have an alkyne. All right, for the next group, we want to say whether it is saturated or unsaturated. Remember, saturated has only single bonds. Unsaturated will have double or triple bonds. So if you see a double bond somewhere, unsaturated. If you see a double bond, unsaturated. Only single bonds, saturated, and double bonds, unsaturated. All right, and then the next question again is the same idea. We have an alkane, because it's all single bonds. Because we see these double bonds, but we see them in a ring-like format, we're going to call it an arene. Here we have a triple bond, that's an alkyne, and here we have a double bond, this is an alkene. All right, so I hope those make sense. All right, next thing that we're going to do, this is a little bit tricky. We're going to be looking at these ball and stick figures. I apologize, they're a pain in the butt, and you're gonna have to move them around in order to see them in decent shape. But we're going to notice how it's a 3-dimensional structure associated with them. And so what you're going to see is you're gonna try to depict this 3-dimensional structure. Like I said, they're a little bit of a pain in the butt to see, but each color is representing a different atom. So if you look here, and we were to see this green-like structure, this is going to be representing carbon. I guess it's like a robin's egg blue, but the robin's egg blue is depicting a carbon. The white are going to be hydrogens, and the reds are going to be oxygen. So let's draw this out to make it a little bit easier. We're going to see that we have, and I'm going to show the hydrogen in purple. We have a carbon, we have an oxygen, another oxygen, and a hydrogen. So let's try to bond these together. We're going to have a single bond between carbon and hydrogen, double bonded oxygen, because remember, we want to get 4 bonds around carbon, and then we're going to have this OH group. So we're going to be looking at a carboxylic acid. So we're going to find the guy that has that carboxylic acid, and that would be this guy here. Now, don't let these dots on the side worry you. These are called lone pairs, which just mean that they are electrons that are not in a bond. So you'll see them around oxygens, or you may see them around nitrogen. All right, next guy that you're going to see. Again, we'll do carbon in blue to make sure this makes more sense. We're going to see that there are 3 hydrogens around it. And again, I'll show it in purple. We have an oxygen, and then we have another hydrogen. And again, you can spin these guys around if needed, so you can see a little bit more detail to them as well. All right, so let's bond these guys up. We're dealing with an alcohol here. So we're going to look for the CH3OH. That'd be this guy here. All right, next one that we're going to look at, we have our, it looks like 3 hydrogens, a carbon, another carbon, an oxygen, And let me do this here. I'm going to put it this way. OH. All right, so again, those 3 hydrogens are going to go around carbon. This guy has 4 bonds around this carbon. Now we got to deal with this carbon. We'll have 1 to that OH group, and then we'll have that double bonded O at the top to make sure that there are 4 bonds around this carbon, because carbon always wants to have 4 bonds around it. All right, so again, looking here, we're looking at a carboxylic acid again, and it will be this guy here. And then finally, last but not least, we have all these carbons and hydrogens. It has to be this one. All right, so we'll submit our answer and we're good to go. What I would suggest doing is, if you are at home working on this, grab some colored pencils. That way you're going to be able to depict the colors, and this will make life a little bit easier when you're running through these homework problems. All right, so same thing, next one here, we want to look at the condensed formula, and we want to compare it to the expanded formula that we're going to see. So CH3, CH2, NH2, this one's pretty straightforward because you just look for the one that has the NH2. It has that amine group. Same thing with the one like this, again, because we want to know that we have carbons that have those 4 bonds around it. CH2. And then we have that OH. So again, looking at an alcohol, we're seeing that guy here. All right, next one. Again, we have our CH3. So I'll draw that out here. So you have 3 hydrogens surrounding that carbon. OCH3. This is what's making what's known as an ether. So there's a carbon on either side of that oxygen. And that would be this guy here. And then finally, we would be dealing with this carboxylic acid here. All right, so again, you're looking at that expanded formula and structural formula, and we're going to make sure that we see those differences. What happened here? This is correct. Oh, let me clear it. Okay, amine, alcohol, ether, and carboxylic acid. I think I hit the button too many times. Submit our answer, and we're good to go. All right, and same idea here. We'll have our ether. Here we would have our aldehyde, our carboxylic acid. Oops, clear. We'd have our ether, our aldehyde, our carboxylic acid here, and our alcohol group here. Submit our answer, and we're good to go. All right, next thing that we're going to do is we're going to be looking at what are called cycloalkanes. Cycloalkanes, an alkane tells us that they're going to be all single bonds, but cyclo tells us that we're going to see it in this ring-like format. So as those aromatic compounds are shown. Again, we're going to be looking at these ball and stick figures. What we're going to see is that the gray is depicting carbon, the white is depicting hydrogen. So you can rotate this around and kind of see a clearer picture. Try to do your best with it. And what we're going to see is we have sort of a ring-like structure in a triangle. And then there are carbons coming off of it. Now, what this looks like here, again, and what this is showing you is that at each one of these points, there's a carbon. And remember that carbon wants to have 4 bonds around it. So depending on the bonds, you may have 1 carbon, you may have 2, or you may have 3. So what we're going to do down here at the bottom is we're going to circle all that apply. Again, you're going to look for the one that has a triangle unit to it. And we're going to see that we have those 2 side chains coming off. So that would be this guy here. But this guy also represents the exact same thing. One, we're just seeing it in this more condensed formula. One, we're going to see in a skeletal formula. So we can submit our answer and we're good to go. Same thing with this one down here at the bottom. We have our triangle shape, and then we're going to see that we have a CH2 and a CH3 coming off of it. So it would be this guy here, but it would also be this guy here, because they'll show you in a condensed structure, and again, they're going to show you in a skeletal structure. And then finally, again, for this one here, we're going to see that we have 1, 2, 3, 4, 5 in a ring with one CH3 coming off. So that would look like this guy here, but it also looked like this guy here. Submit our answer, and we're good to go. All right, now we're going to get into the nitty-gritty details of naming. So when we're dealing with alkanes, we care about the number of carbon atoms. And our first goal will be that we want to make sure we find this longest chain. So we use some prefixes for naming hydrocarbons. 1 is going to be meth, 2 is going to be eth, 3 is going to be prop, 4 will be bute, 5 will be pent, hex will be 6, hept is 7, oct is 8, non is 9, and dec is 10. And because they are alkanes, ane is going to be the very ending that we will use. Then that depicts that we have all single bonds. If we were to have a double bond somewhere, we would name it with an ene at the end. And if we had a triple bond, we would name it with ine at the end. Now, if we happen to have a aromatic compound, we will name these with cyclo in front to show us and depict that we see a ring-like structure. So for instance, this example that they have down here at the bottom, you have a 5, 1, 2, 3, 4, 5. You have a 5 carbon chain in a ring, and they're all single bonds. So we call it cyclo to depict their ring, pent for 5, ane for single bonds. And then we will have some little side chains are called substituents. And these groups that we're going to see have different names. If you see 3 in a row that are like a chain coming off, but they're not part of our longest chain, we call this propyl. If you see this CH and there's 2 other kind of methyl groups next to it, we'd call this isopropyl. 4 in a row would be butyl. This 3 with 1 kind of in the middle is isobutyl. We got a sec-butyl going on here, and we have a tert-butyl. And if you need some help with these, again, if you utilize this little basic decoding guide, they kind of show you this idea of how to understand the idea of parent chains, side chains, and how to start to name them. I would really suggest using this. This will be kind of helpful to sort of help with the decoding and making sure that this sort of makes sense as to how we name them and what it looks like. And I hope it makes a little bit more sense. Okay, so what we're going to do here is we are just going to name each of the following compounds. Here we have CH4. We only have 1 carbon. And again, it's going to be all single bonds. So 1 carbon would be meth. And because it's all single bonds, we end with ane. So this is methane. Here, what we're going to see is that we have 3 carbons. So this would be prop. They're all single bonds. So it's ane. And they're in a ring-like format, so we call it cyclo. So this is cyclopropane. All right, down here we have 1, 2, 3, 4, 5, 6 carbons. So 6 would tell us hex. And because they're all single bonds, we would say ane. So this would be hexane. All right, next one that we're going to see, we want to name the following groups. So again, this is what's going to be helpful to understand those side chains and understanding how we name them. If there's 2 for a side chain, we would call this an ethyl group. If you have 1 carbon as a side chain, that would be your methyl group. And this guy here, from understanding those different groups on the side, this would be isobutyl group. Submit our answer, and we are good to go. All right, and now we're just going to practice naming. So now we're going to practice naming with the idea of understanding the number of carbon atoms present, looking for those branch changes and those substituents. And we want to make sure we say what the substituent is, what carbon are they located on, and we want to put them in a specific order. So here are some rules for the IUPAC naming. Again, the first thing that we have to do is find our straight chain and find the longest chain. Next, what we're going to do is we're going to mark any of the branch chains, and we're going to give the root based upon that same prefix, if you will. We'll just add YL to the end. Then what we're going to do is we're going to see how they're bonded. So again, we want to make sure we understand that we want to give them the lowest number. And again, we want to see if it's an alkane, an alkene, an alkyne. If you have two or more of different substituents, you name them in alphabetical order. And it doesn't matter the position, you just name them in alphabetical order. And then if you have multiple of the same substituent or that branch group, you have to make sure to give some prefixes to say how many that there are. So let's give some examples. Okay, so here we want to look at the traditional IUPAC naming. And IUPAC naming is the standard naming that we do for these organic compounds. Let me get this a little bit bigger so we can see it in a little more detail. Okay, so we want to pick the longest chain. 1, 2, 3, 4, 5, 6, 7. So far, our longest chain would be 7. But let's double check really quick to make sure that this wouldn't be our longest chain. 1, 2, 3, 4, 5, 6. Nope, that won't work. So our longest chain would be here. 1, 2, 3, 4, 5, 6, 7. So we're going to name our chain. Our chain is 7, so it would be hept. And because it's all single bonds, we're ending in ane. But we still have to account for this group up here. This guy here. So we not only have to identify the group, and this guy here would be a methyl group, but we have to tell you where it is and what location it is on the carbon. And it is on the 3rd carbon, so we would say 3-methyl-heptane. Submit our answer, and we are good to go. All right, now we got another ball and stick formula. Again, these are kind of a pain in the butt, but you can rotate it out to sort of see. So what I would suggest doing is actually drawing this out so you can see what it looks like. And again, I'm going to draw it in the skeletal formula. So remember, every point is going to be showing you and indicating a carbon. So let's try to name our longest chain. We have 1, 2, 3, 4 carbons as our longest chain. So this would be bute for 4. And because it's all single bonds, we end in ane. But now we have to take into account this group here and this group here. They are both methyls. So because we have 2 methyls, we have to write di for 2, methyl. And now we have to indicate where they're located. So they are on the 2nd and on the 3rd carbon. We put a dash, and we are good to go. So like I said, I would suggest that you draw these out on a separate piece of paper, have them make a little bit more sense. And I would even probably put some colored pencils in there just to make it a little easier when you're trying to name these guys. Okay, another ball and stick figure. So again, my best suggestion is to draw this out. 1, 2, 3, 4, like this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then this guy here has couple methyls sticking out. So again, we'll name our longest chain. Our longest chain would be pent. And then again, it's ane because they're all single bonds. Now we have to find out, again, with these groups, what they're going to be called. This is going to be that we have these methyl groups. And because we have two, we'll say dimethyl. And they're both on the third carbon. So we put 3,3 dimethyl pentane. Because again, we have to show their location, how many we have, what's the name of them, and then again, name that longest chain. And we are good to go. All right, keep practicing these. I hope these make a little bit more sense, and we're going to be moving on. Number 7 is going to help again with naming alkanes as well, and we're going to be practicing putting them in a ring format as well. If you do have the ring is going to actually take the precedence as the longest chain. So just be careful with that. If you have a cyclo, and that usually will be the size of the ring, and again, if it happens to be longer, that will be your chain instead. So let's practice this a little bit. So this is going to be a little bit different than what we've seen previously. We need to just draw the structural formula for pentane. Pent tells us that we have 5 carbons, so we want to make sure to draw 5 carbons. And what we can do is we can add these lines and actually make our chain. Right now we have 4 carbons, and we need to add 1 more. They're all single bonds, so this is actually good to go. Submit our answer. We're ready. All right, next one that we're going to do is we're going to draw the structural format for 2,3-dimethyl butane. Again, start with that butane first. Butane is 4, so 1, 2, 3, 4. And now we want to add in our 2,3-dimethyl. So that means that we're going to add a CH group to the second and add a CH group to the third. Submit our answer, and we're good to go. Same thing here. We're going to do 4-methyl heptane. Start with the heptane first. Again, 7 for hept, all single bonds. So 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And now what we have to do is we have to add that methyl to the 4th carbon. 1, 2, 3, 4. And we are good to go. All right, same thing. We're going to be practicing naming, but now we're going to be naming our alkenes. Plus, we're also going to be adding in what are called isomers as well. So getting to this portion here, we're going to be talking about isomers. And the isomers are going to mean that they have the same molecular formula, but they have a different makeup. So down at the bottom here, these are all constitutional isomers. C6H12 and C6H12, they have the same molecular formula, but their structural formula is different, meaning how they're arranged is different. Cyclobutane to methyl cyclobutane, they all have the C4H8, but their structural formula is going to be a little bit different. So what we're going to do is we're going to try to find those isomers of butane. So butane looks like this by the time it's all said and done. There's 4 carbons around it. So 1, 2, 3, 4. And what we're going to see is that we have CH3, CH2, CH2, CH3. So we need to come up with a plan that gives us C4H3, 5, 8, 10. So we want to see if any of these are going to work that same way. First of all, if you were to look at 2,4-dimethyl pentane, just automatically looking at this, pentane you know is C5. So that's not going to work. But maybe this 4-methyl heptane would work. But wait, heptane, C7, not going to work. But let's try this 2,2-dimethyl propane. Maybe this would work. So propane is going to be 3 carbons. And then we have 2,2-dimethyl, so that would go on here to add 2 more. Wait, that's C5. That's not going to work either. So let's try this 2-methylpropane. So propane again would look like this. And then it tells us that we have a second methyl, that's CH3 coming off here. So now we have C4 and then 3, 6, 9, 10. So this is the only constitutional isomer that's going to work here. Submit our answer and we're good to go. Okay, so same idea here. We have pentane. So CH3, CH2, 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 CH3. Again, pent tells us 5, ane tells us they're all single bonds. And remember, carbon always wants to have 4 bonds around it. So this is going to look like this: C5, H5, 10, 12, H12. So we have to find an isomer that's going to be C5H12. They're just arranged a little bit differently. So let's try 4-methylbutane. Butane tells us that we'd have CH3, CH, CH2, CH3. And then the 2-methyl will go on top here. So this is how it would be arranged. The butane tells us that we have 4 single bond ane, all single bonds, no double bonds. And then the 2-methyl tells us that we have this guy on our second carbon. So now we want to count it out. We have 1, 2, 3, 4, 5 carbons. And we have 6, 8, 11, 12 hydrogens. So this guy would work as an isomer. All right, let's try cyclopentane. So cyclopentane tells us that we would have a 5-carbon ring, and the cyclo actually gives the depiction that it's a ring. So again, 1, 2, 3, 4, 5 carbons. And because carbon wants 4 bonds, there's 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here. So we'd have C5, H2, 4, 6, 8, 10. That's not going to work. We want a C5H12, so cyclobutane isn't going to be able to work. We also know that this 2,2-dimethylpentane can't work because pentane would be C5, but if you had 2 additional methyls, that would add on 2 more C's, 2 more carbons. So that's not going to work. But let's try this 2,2-dimethylpropane. So again, propane is going to look like this. So we have our propane, and then we have our methyl group sticking out here. CH3, CH3. So we have 1, 2, 3, 4, 5 carbons. And now we have 3, 6, 9, 12 hydrogens. So this guy would work. We'll submit our answer. Oops, wrong one. We'll submit our answer and we're good to go. All right, for number 9, this is going to be asking some questions about boiling points and melting points, as well as number 10, we'll be talking about solubility. When we think about boiling points for alkanes, so when we talk about these, the boiling points of alkanes are going to increase with the increasing number of carbons. So the more carbons you have, that boiling point is going to increase. And this is due to what are called intermolecular forces. Now, what's going to happen as well is if you have more